Ready for this? We're diving deep into a paper that kind of set the stage for, well, pretty much everything we do with computers.
Definitely a landmark paper.
Alan Turing, 1936, on computable numbers with an application to the Entscheidungsproblem.
Catchy title, right?
Well, it's not exactly like reading material, but that's what we're here for. Unpack it. So anyone listening who's ever wondered what makes computers tick,
Or even just what computable really means.
this is the deep dive for you.
This paper, it's like Turing reached into the future and laid the foundation for computer science.
Okay, so not to state the obvious or anything, but this was way back in 1936. We didn't have computers like we do now.
Not even close. Turing was grappling with these fundamental questions about what machines could even theoretically do.
And that's where the Turing machine comes in, right?
Exactly. This wasn't about building some physical machine. It was a thought experiment, a model for computation.
A model, so like a blueprint.
Sort of. Imagine this. A really simple machine. There's a long tape, like ticker tape, divided into squares.
Okay, I'm picturing it.
And on those squares, you can write symbols. The machine has a little head that moves back and forth, reading and writing symbols.
And it follows a set of rules.
Exactly. The rules tell the machine what to do based on the symbol it reads. Like, if you see a 1, move 1 square to the right.
Okay, so it's all based on symbols and rules.
Surprisingly, yes. Turing showed that with the right set of rules, this simple machine could perform any logical operation.
Any, you mean like addition, subtraction?
Yep, all of that. Even complex calculations, stuff we need computers for today. Turing proved that if you can break a problem down into a sequence of logical steps, a Turing machine can handle it.
Wow. So in a way, he invented programming before computers even existed.
You got it. But it gets even wilder. He didn't stop at just a machine. He came up with the idea of a universal machine.
A universal machine. Okay, now you have to explain this one.
Picture a Turing machine that can simulate any other Turing machine.
Wait, what? How?
Remember those symbols on the tape? Turing realized you could use those symbols to describe not just numbers, but the rules of another Turing machine.
So it's like feeding instructions to the universal machine.
Exactly. It's like giving it a blueprint, and the universal machine could reconfigure itself to become that machine, running those rules.
That's insane. It's like he came up with the concept of software. It's like he's thinking a whole level above what anyone else was even considering back then.
It's incredible, really. He wasn't afraid to ask the big what-if questions, and one of the biggest ones he tackled was about the limits of computation.
Okay, so we've established that Turing machines, even universal ones, aren't magic.
Right, they're powerful, but there are some things they just can't do.
And Turing figured that out too.
He did. He proved that there are some problems that no algorithm, no matter how complex, can solve. Unsolvable problems.
Unsolvable. So even with a super-duper Turing machine, some things are just impossible to compute.
Exactly. And he illustrated this with something called the Entscheidungsproblem.
Entscheidungsproblem. This is intimidating.
It's a mouthful, yeah. Basically, it was this big open question in mathematics at the time. Could you create a process, an algorithm, to determine if any given logical statement is provable?
So, like a truth teller for math. You feed it an equation, and it tells you if it's legit or not.
Kind of. A lot of mathematicians were hoping for something like that, but Turing proved it was impossible. No such algorithm exists.
Whoa.
Yeah.
Even with infinite time and computing power.
Even then, it's not about the physical limitations of machines, but about the very nature of logic and computation itself.
How do you even begin to prove something like that?
Well, he used his Turing machines, of course. He showed that if such a truth-teller machine did exist, you could use it to solve a particular problem about Turing machines themselves.
Okay, now you're going to have to walk me through this.
Imagine you want to know if a specific Turing machine, given a specific input, will ever halt or just keep running forever.
Right, kind of like when your computer freezes up.
Exactly. Turing proved that if you could solve the Entscheidungsproblem, you could use that solution to figure out if any Turing machine would halt or run forever.
And that's impossible, right? We can't predict the future of every single program.
Precisely. And since we already know that's impossible, Turing showed that the Entscheidungsproblem must also be impossible. It's like a domino effect of impossibility.
So Turing found the boundaries of what's computable by proving what's not computable.
And in doing so, he actually ended up connecting with another really important concept, Gödel's incompleteness theorem.
I've definitely heard of that, but I'll admit it's a little fuzzy.
Basically, Gödel had shown that within any formal system of logic, like mathematics, there will always be true statements that you can't actually prove within that system.
So there are some things that are true, but we can't prove they're true.
Exactly. And Turing's work on unsolvable problems sort of echoed that idea. Even within the realm of what's calculable, there are still limits to what we can know for sure.
It's kind of a humbling thought, isn't it?
Yeah.
Even with all our fancy computers, there are some mysteries we may never be able to crack.
Absolutely. But that's part of what makes Turing's work so fascinating. He didn't just define what computers can do, he also revealed the elegance and depth of what they can't.
Okay, but all this talk about what machines can't do, let's get back to what they can compute. Specifically, those computable numbers Turing was so interested in.
Right, because that's at the very heart of his paper, isn't it? So computable numbers. It's all about what a Turing machine can actually, compute. If a Turing machine can calculate it, it's a computable number.
Makes sense. But give me some concrete examples. What kind of numbers are we talking about here?
Well, the obvious ones first, like the numbers we use every day, 1, 2, 3. Those are easy for a Turing machine to handle.
Okay, so integers, check. What about fractions?
Fractions too. Any number you can represent as a ratio of 2 integers. Those are computable.
Got it. But it gets a little more complex than basic arithmetic, right?
Oh yeah, it gets interesting. Turing showed that even some really intricate numbers are computable. Like, take real algebraic numbers.
Algebraic numbers. Refresh my memory.
Basically, they're solutions to polynomial equations, like x squared minus 2 equals 0.
Right, so the square root of 2 would be an algebraic number.
Exactly. And even though it's irrational that decimal goes on forever, it's still computable. Turing showed that any number you can define as the root of one of these equations, it's computable. And get this, even pi.
Pi, you mean like 3.14159 and so on.
The one and only, that never-ending decimal, totally computable.
But how can a machine ever calculate something that literally goes on forever?
It's about being able to approximate it to any level of accuracy you need. We can write an algorithm to get as many digits of pi as we want. Same goes for another famous one, Euler's number, E.
So even these fundamental constants of the universe, these seemingly infinite numbers, are within the realm of what's computable.
That's right. And that's a pretty amazing insight, isn't it? It shows just how powerful Turing's model of computation really is. But here's the real head-scratcher. Turing also proved that there are infinitely many numbers that are not computable.
Hold on, wait. There are numbers out there that no computer, no matter how advanced, could ever calculate. How is that even possible?
It's one of the most mind-blowing implications of his work. He basically showed that the set of computable numbers, as vast as it is just a tiny drop in an ocean of numbers that lie beyond our computational grasp.
So there are numbers out there that we can't even describe or define with an algorithm. We can't even wrap our heads around them.
It's kind of a mind-bending concept, right? These non-computable numbers, they exist, but they exist in this realm beyond our current mathematical and computational tools. It's like we've mapped out this whole world of computable numbers, but just beyond the horizon, there's this vast, unexplored territory of numbers we can't even begin to comprehend.
It's like a whole secret universe of numbers hiding in plain sight.
And that sense of mystery, that there's still so much we don't know, that's part of what makes Turing's work so fascinating even all these years later. He didn't just give us the blueprint for the computer age, he also opened our eyes to the profound limits of what we can compute and maybe even what we can know.
It really makes you think, doesn't it? Even with all our technological advancements, there are still some mysteries we may never be able to solve. There's a certain beauty in that, I think. So to everyone listening, next time you fire up your computer, remember Alan Turing and the incredible legacy he left behind. A legacy that goes way beyond ones and zeros, into the very essence of what's knowable and what might forever remain beyond our grasp.